Okay, and let us get ourselves going for today. Today, what we would love to do is actually talk about the building envelope. In particular, kind of think about how all these different elements that are part of the envelope really factor into the notion of how much heat is flowing in or flowing out of the building, and really think about kind of what the sources of heat are. Think about how conduction and radiation sort of work together, and how ultimately we design envelopes to sort of try to harness those forces and make the right things happen. So that's where we're going to go today, and I'm actually gonna we're gonna be a little scientists today. We're gonna go through and kind of build this up a little bit, like stepwise, in terms of really trying to understand the behavior of kind of sort of a very simple black box, or just a box, and what the effects of the weather on that, and then kind of get a little bit more complex in terms of thinking how that actually translates into building envelope elements. Okay, so we're going to start sort of on the simple side a little bit. So to do that, what I would love you to do is, I can get rid of that for a minute. Okay, go ahead and open up Ecotect. Ecotect being the program that we installed last time together. It should be on most of your machines. And if you can open that up, it's going to be a useful tool for us to work with. What we're going to do in Ecotect is just sort of model a little basic box, and with that basic box, just go through and figure out, kind of what the effect of all these weather changes are on that box. So you can either open Ecotect, you can also do this in Revit, but I'll do it in Ecotect first, and then we'll show you how to do it in Revit too. And we're going to just basically go through and place a box in a specific place on the Earth, and I'm just going to start thinking about really what the forces on it are. So if you have the Ecotect open, and please do if you can, go ahead and open that up. What we're going to do is just create a little box-like surface for ourselves. I think there might even be the opportunity to do that right here. That's a whole zone. Go back to the box. I'm going to go through and create some walls. Oh, let me check to make sure if my units are set up properly, just because I tend to like to work with US units. So I'm going to go localization, feet and inches. That looks pretty good. Okay, I will let that be. So I'm just going to go through and create a box. The dimensions of this aren't all that important, but let's go ahead and say, like 20 feet or by 20 feet, something like that. Just something that's enough to be big enough so that we can sort of see the effect. I'll come back this way, approximately 20 feet. Come back down here. You can see when I sort of get parallel, the little inference line will show me that I'm going to line up with the other one and close the point there. And I'll turn that into a closed surface. Okay. So far so good, not a whole lot special going on there. Let us also go ahead and kind of put a top and a bottom on this, because we'd like to enclose the box. So I'm going to choose the plane tool and just kind of put a little bottom to this. Okay, and I'll also go through and make a top on it. So hopefully we're doing pretty good there. We have this basic little box in there. It really just has, it's one region right now. It's just kind of like this little closed thing that's happening right there. And what we're going to do is actually go through and just kind of think about really what the effect on that box is of the weather as we go through and kind of apply a weather file to it. So let me do this. I'm going to go through and for this model, locate it somewhere, saying site and location. And again, we can choose most anywhere we want to. I'm going to go through and let me grab a weather data file from someplace relatively close around here. So we can go to, in the US, to San Francisco if we want to. Or maybe I'll go a little further north, Seattle, Washington. And what will happen is the latitude, the longitude, those will all be adjusted so that they're appropriate for Seattle, Washington. I'm not going to give it any orientation right now. But even what we've done so far, there's a fair amount of data applying to that box. Okay, so I'm going to go back to the little visualizer so I can sort of see it. It's just kind of a nice little enclosed surface. So again, we have the 3D editor for kind of creating the shapes, the visualizer, and then there's this little analysis tab, which is the one we're going to be playing around with next. Just talk about the analysis tab and how we can actually go through and use that. So under the analysis tab, there are really all sorts of interesting things going on, including just this whole notion of like temperature profiles, just all sorts of stuff in there. So let's see if we can actually sort of discern a little bit about what's going on in here and really what the effect is, of, or what we can actually see in the satellite. So let's kind of take a look at this. There's the outside temperature. Let me run the calculator. This doesn't look like good data. This looks like it's not quite ready yet. Maybe it's not really. That seems so bad. Well, oh no, it's 1st of January. No, it's updated. Okay, if we look at the hourly temperature profile, for example, on the 1st of January, which is where we are right now, you can see that if we're in Seattle, that the hourly temperature profile at somewhere around midnight looks like it's somewhere around 30 degrees. It's the blue line that's kind of popping around in here. The blue line's kind of following through. It's pretty cold around 30 on January 1st. As we get up towards 11 or noon, it's actually getting a little bit higher, getting up to around 40 degrees, and then tapering off back down again towards 30 degrees, a little bit later in there. Okay, that's the blue line. The blue line is actually indicating the outside temperature. Being solar, that's actually the amount of direct radiation we're getting from the sun. That's during the day. So you see, from midnight to late in the morning, it's tracking right at 0. Then late in the morning until around 5 in the afternoon, 5:30 in the afternoon. You have a peak around noon and kind of tracking back out again there. So this is what it looks like in January. Let's kind of switch it up a little bit though. And I'll do that by just up here in the menu bar at the top, going ahead and switching to a different month. Let's just change it to like June or July or something like that and look at how different the data is. So here we are in June 1st. You'll sort of see that it's kind of an interesting profile there. Looks like around midnight it's still relatively warm. It gets cooler in the early morning hours, 4 to 6, then getting back up into the 60s in the midday. And then kind of tracking back down again. See the solar, the little more solar energy. It starts a little bit earlier, like around 6 in the morning, trailing off somewhere around like 16. It's still trailing off around like 5 o'clock in the afternoon, something like that, in terms of the amount of solar energy. Okay. See about the wind speed, a lot of different things in there. But you sort of see the profile of the energy. And if I switched over again to, let's take a look at it in the middle of July, you see the temperature is a little bit higher still. It's interesting. It's cooler in Seattle than I think of it as being. At least the average temperature data kind of shows it being that way. So let's think about really what the effect of this is really like on our little box. And it's like mid-July is really not necessarily the best time to look at it. Let's go back to January and we'll sort of think about what the effect is over there. Okay, so if we have our little box and it's kind of hanging out there, looking ever so lonely on the landscape there, we won't put any people in it yet, we're just going to have the box out there. And we think about the temperature inside that box and what's going on. Now, if we want to inhabit that box, if we want to actually kind of be hanging around inside there, what might be sort of a good temperature range that we consider to be allowable or comfortable or tolerable even, something like that. So how cold do you think you get in there to the point where we'd still sort of consider it like, tolerable? So, like, what's a good wintertime temperature? What do you like the room temperature to be during wintertime? 65 or 63. Okay. Now, that's actually cool to me. It's kind of cool that, it's interesting that you'll actually accept the temperature that cool. I kind of think that's kind of interesting. What would happen? Okay, so we find that actually people's comfort level, and the whole way of looking at people's comfort is really related to a number of different things. Because part of it's just sort of the raw temperature, the actual absolute temperature. Part of it's related to sort of humidity in the space. Part of it's related to the whole notion of the air moving through the space. All these things kind of work together to create your overall level of comfort within the space. So, they all kind of factor in together to create really what's considered an acceptable climate range within the space. What tends to happen is, like even in warmer environments, if it's relatively warm, okay, but you can introduce either a little bit of air moving through the space, or even sort of, dry air actually sort of helps too. It's this whole notion of like there's different ways of moderating against the sheer effects of temperature. It's also sort of a cultural thing too. We have different expectations about what temperature is, depending on our, culturally how we were raised and what our expectation was from our own homes. Okay, so if we wanted it to stay somewhere around 60 degrees in this box through the day, okay, and I went back and I looked at
kind of this temperature profiles and what's happening during the day. Okay, so let me try this. Here's our box. That's just kind of a little section of our box. Okay, it starts out 60 over here. Okay. It's going to start out around midnight, around 30 degrees out here. Okay, and we see what's going to happen with the temperature profile through the day. What's going to happen to the temperature in that box through the day as we kind of move through this? So it's starting around 30 outside, it's 60 outside. Okay, you know, as we get to like 6 in the morning, it still looks like it's 30 degrees outside. What do you think is going to happen inside between now and 6 in the morning? It starts at midnight. Is it going to stay 60? Nah. Okay, so what's probably going to happen? It's probably going to get colder. That temperature is probably going to drop. So if I looked at the temperature profile in the box across time, it's probably going to start up here at 60. But what's going to happen is it's going to start dropping. And why is it dropping? Because you basically have some sort of differential between the inside and the outside. And basically heat's going to flow one way or the other. So if it's colder outside than it is inside, heat's going to try and flow out. If it's warmer outside than it's inside, heat's going to try and flow in. Okay. So what's going to happen is, over time, it's going to start dropping. Hanging around out here, it's going to be 30 degrees. Oh, up here in the middle of the day, it's going to get up to 42 degrees. But even at 42 degrees out there, it's going to get cold. Yeah, it may start warming up a little bit. It's a little unclear. You know, there's a question like, do we think that by 6 in the morning or something like that, is it going to get down to 30 degrees? You know, it may or may not. It kind of depends on what the thermal characteristics of the wall are. It's going to start dropping, but depending on how quickly heat is flowing out of the building, it may or may not get down there. It may not get to 30. It may only get down to be 50 degrees or 40 degrees and kind of keep on dropping. But it's going to be dropping as long as the temperature on the outside is colder than we want. Okay. What's happening up over in here? By the time we get up to noontime, the temperature is going to be around 42 degrees. Okay. That might bring it back up to around 42 degrees. Or if the temperature inside the building is lower and it's 42, what will happen in here if it was like 30 inside the building and it was 42 out here, we'd start having the other thing. Heat would start flowing into the building and the temperature would start rising again. So it might be picking up a little bit. Will it get up to 42? It really just kind of depends on what the thermal characteristics are, you know, whether it's actually going to get right there. If there was no wall on this side and it was completely open, we'd track perfectly with the outside weather. But what tends to happen is because the walls have some sort of surface which has some characteristics to it which slow down the flow, it's not a free flow, you tend to have this lagging behavior. Like the inside temperature is going to try to match the outside temperature, but it's always going to lag behind a little bit. Okay. Now, if we just kind of left this thing steady state January 1st and kind of kept on replaying this day after day, what would ultimately sort of happen to that temperature inside? Would it ever get back up to 60 degrees? Yeah, it's going to probably end up, if we just kept on replaying this day, just somewhere between, 30 and 40, just somewhere in there. It's going to ultimately kind of normalize itself out. It'll swing up, it'll go down, but it tries to sort of get to a steady state. That is, if we're just looking at the outside temperature and what's going on. So wintertime, a little bit harder in terms of anticipating what's going on. Let me switch to a different climate and kind of think about really what the effect would be there. So I look over to July instead, and what do we got going on here? Here it's kind of like 60 degrees through most of the night. That's kind of doing pretty good. During the middle of the day, it's getting up to 70 degrees, and then it's kind of cooling back down there. So slightly different behavior here. Again, the building's going to lag a little bit relative to what's going outside, but if I wanted the temperature to stay right around 65 or 68 or something like that, this might not be too bad. It'll be a little bit cool in the morning, might get a little bit too warm, but whether or not we actually get there depends on whether the windows are open. And then it'll kind of start cooling back down again. And, that's actually pretty good. We could probably, not allowing for like any other introduction of heat, live pretty comfortably in Seattle during the summertime. Okay, and actually be okay. Yeah, very different when we switch to other parts of the world though. So for example, when I go switching over again to a place like, oh, where do I want to go to? Let's go to, where did I find last time? I tend to like to go to India as being an example of a very warm place. Okay, and I go back over and I take a look at those temperatures. Let me recalculate that. Okay, you see we have, this whole behavior where at its coolest, at 4 in the morning, it's getting down to 82. But up here in the midday, it's actually late afternoon. It's getting to be close to 100 degrees or something like that. So here we have sort of a different kind of problem. In this sort of case, really what's happening is we'd like to kind of keep the temperature in here somewhere around 60. Okay, but outside what's going to happen is the temperature is going to be very hot. So what will happen over time at a steady state is that, if we just keep this up for several days in a row, eventually this building is going to normalize somewhere around 90 degrees or something like that, which again is probably going to be too uncomfortable and we'll be complaining that's hot and things like that. So what we tend to do because of this is actually try to go through and introduce some sort of mechanical system to them. Because really, as a building goes through and swings between highs and lows, as the building temperature goes through and swings between kind of these low temperatures and these very high temperatures, there is some sort of comfort range that we like. Somewhere here, between, that's not bad, marker. Between the 30s and the 90s up here, there's this comfort range that we want to try to keep the building in. And everyone's a little bit different about what those set points are in terms of how cold you want the space to be, or how cold does the space have to be before you start heating, and how hot does the space have to be before you start cooling. Everyone's a little bit different. If we assume that 65 was a lower limit or something like that, and how about on the upper side? How warm could the room be before you really have to turn on the air conditioning? There's no right answer. Is 80 degrees? 82 degrees? Something like that? There's some temperature that just starts to make people uncomfortable. Let's say it's 82 degrees. So what happens is then as we go through and we're within this comfort zone, let's think about, if we're in the comfort zone, somewhere between the heating and the cooling, okay, kind of independent of what's happening here, we could always just open a window and kind of just take advantage of the natural ventilation, as long as we consider to be comfortable. When it's up here, we need to basically introduce cooling to go ahead and bring the temperature so it's down within that range. Okay, on the other end of it, when it's kind of hanging around down in here and it's cold, we introduce the heating. Okay, so we want to bring it back up to that range. So that's really when we start thinking about mechanical systems and really where a lot of the energy cost is going and stuff like that. That's what we're really trying to do. It really has a lot to do with the range that we set, what the temperature is, and what the difference between the temperature naturally outside, the range that we want to be in is, and how we can go through and kind of affect that. Let me see if I can make something. Let's go to analysis. Let me try this passive gains and see if we can make this work. Okay, I don't have a zone. I need to create a zone for myself. This is something that actually comes out of when I go through and do it directly out of Revit. Oops, I want that one. See if I can make that work now. Hang on just a second. Nope, still not there. Let me do it out of Revit. It'll make it easier for me. Okay. Let us do this. We are going to go back over to Revit for something. We're going to create a box over there, but I'm going to do one that gives me just a little bit more control. Okay, so I'm going to open up Revit and we'll do it over there. We need to go ahead and have something called a zone. And again, I'm not all that familiar and don't really like working in Ecotech in terms of doing the drawing. So I'll go ahead and bring it in from Revit because I think that'll be a little bit easier. I'm going to say just make a new project here. Architectural template. I'm going to create that same little box, but this time I'm going to go through and give myself a little bit of zone information to work with. So let's do this. I'm going to go through, and I can do this one of two ways. I can go through and create this out of real building elements, so I can create it as a conceptual surface. I'm just go ahead and do it out of real building elements, because I think that's really where we want to go with this. Let's go ahead and create a really simple little box-like structure, okay, and bring it over in that same sort of way. But then we're going to start playing around with its material qualities. So to create that real simple little box, I'm just going to go through and create some sort of architectural walls. You can leave them generic if you want to right now, or choose a material property. I'm just going to leave them generic right now, since I just think of it as sort of a box. I'm going to make that go from level 1 to level 2, and just kind of draw some sort of little box there. Let me show that in 3D. Okay. Again, because it's a box, we need to go through and close the top and the bottom. And I will do that by adding a floor to it. I'll just make it a generic floor for now, picking these surfaces on the outside. And also I'll put like a flat roof on it, just so we have something to enclose it. And then I will also upload this to coursework, so if you want to, you can actually kind of just hang on. I won't even put any overhang on it for right now. Oops. Although it does have some slope, I don't want that. Let me go through and turn that slope off because I want to keep it very simple for right now. Okay, very simple little box right now. It's very equivalent to sort of what we've been drawing so far. We're going to go through and bring that into Ecotect. How the notion of a zone works in Ecotect, or how we create zones, is actually using something we call a room in Revit. So if we go through and we create a room, let me go through and choose the room tool, and I can just put one inside here. Once I go through and create that room, it has kind of a height to it. I need to do one other thing to make sure that it does compute the top of the space, and that's actually have it compute volumes, not just areas. So I'll turn that on. Okay, and now if I go back and export it, we should be able to take this out and take it over to Ecotect to work with. So what I'll do is I'm going to export this as GBXML. You'll see it'll actually create something. That little blue box on the inside there is really what we have in mind as this surface we're going to be looking at. Let me go ahead and export that. I'm just going to put it on my desktop. Actually, no, I'm not going to put it on my desktop. I am going to put that out in a place where we can actually upload it for you guys to take a look at too. So in session 3, I'm going to say, oh, it's project 1x1l. That's fine. Let me also go through and save this as, I'm going to save the Revit file too. Okay, now I'm going to put those out there. For folks who didn't take 120A and are sort of looking at all this Revit stuff, wondering how it's all working and stuff like that, let me just upload those files to coursework so that you can also go through and kind of follow along. Okay, let me log into this, and I'll put them up there, and then we can all follow along. Because I think it'd be much better if you actually had the experience of actually doing it as we're doing it, and just sort of experience what the tools are like. So, cats. Google Authenticator, since the campus network got broken into. Okay, gotta find where my little Stanford folder is. There it is. Authenticator. My magic code. There we go. Okay, so here in our folder, let me go to materials. Let me go through and we'll add a folder in here for session 3. And then finally in session 3, I'm going to add some files in there. the Revit file, if you want to go ahead and open the Revit file and look at that. And then also add another file. We will choose the XML file. Okay, so those should be up there too if you want to work with them. Okay, so we created this little file, this little box-like file in Revit. The big difference about creating in Revit is I'm going to start having a little bit of control over the materials properties of the different wall surfaces so we can start playing with those. It's also going to go and create a zone for me. That room that it created, that bounding box and the height is going to be useful for us because then we can start thinking about thermal properties of that and how that room is used. So I'm going to put Revit away for just a second. The one thing that I need to do, just to be certain, oops, hang on, is I need to go through and open that file, hang on, in a special way. You stop that. So what I have to do with that XML file, we have that unfortunate thing with the XML file. We just have to open it and basically tell it that its encoding is just a little bit different. I always have to just open it and save it, which is a little bit annoying. It's supposed to be Unifo code. It needs to be UTF-8. It's just a file type thing about just how it's put out from one program and read it on another. You can save that away. And now that I've kind of done that, I can come back over. And what I will do is bring that on in. So I'm going to import it. Let me try this. I'm just going to save it on my desktop instead. Because every once in a while, there's little things that go on between my Mac and my PC. They get a little bit confused. And I try to pretend that there's no difference. But let me see if that's going to make any difference at all. Let me see if that makes any difference. Because the behavior it's giving me is actually, it's the type of thing when it, yeah, it's usually what happens when it doesn't. You get that? Okay, that's it. It's the difference between my Mac and my PC on the Mac file system. Thank you very much for helping me figure that out. Okay, let us see if you guys can open it up and make this work in terms of giving sort of a basic space. It has some generic walls, there's a generic roof and a generic floor, and sort of one space to it. Because if it does, and you get this in here, okay, you have something that looks like that, which is actually not too awfully bad. So again, we can go through and visualize it in terms of what's happening out here. This actually has a space to it. A space is actually, there's the outside space, there's the room itself, and the external shading, although we don't have any external shading here. But when we go through and analyze this box, we'll actually get a little bit more information because what we can start to do is actually sort of think about the thermal properties of the walls and the thermal properties of the room and all that kind of stuff. And let's start just by going through, and again, I will go through and do the model and kind of put it in some sort of space with a weather file. So where did we decide, where did we put this last time? Was it Seattle or in India? Let's try India. Again, doesn't really matter, kind of wherever you want it to be. Okay, I'm going to go back over to analysis, and when I say calculate, it'll go through and do some things for us. So let's take a look at some of the data. There's the whole notion of the hourly temperature profile, and this is in December, and we have a couple different things kind of happening in here. Here in December, you're actually sort of seeing, well, this is, oh, where's my little legend? That was like my little legend. Okay, this is the actual weather data just under thermal analysis. So what's going on here, you're seeing the whole notion of the outside temperature. That's the blue line that's going on there. This black line that you're seeing here, that's actually the zone temperature. That's the temperature actually inside the space, as opposed to what's outside. So what's happening is, oh, it started out warmer than outside in December, okay? As it heated up, after the middle of the day, it actually got pretty warm inside the space, and it kind of started tapering off. It actually sort of met each other. It actually isn't too bad looking in there. You know, it's heating up for a number of different reasons. It's heating up because the temperature is raising outside. It's also heating up because of all the solar energy that's hitting it. We'll talk about that in just a second. Let's go ahead and switch it over, though, and kind of take a look at it in July instead. Okay, so here you see, you know, for the space in June, that's June, there's July. You know, here's the outside temperature. It's kind of coming along. It's a little over 100 degrees, but actually by mid-morning in here, okay, it's actually well over 102, 104, something like that. It's getting pretty warm and uncomfortable in there in that space. So, yeah, not doing pretty good in there. That's because the way we define the space right now, you know, there's not really a whole lot going on. There's not a lot of natural ventilation. There's nothing happening right there. It's kind of just a big closed box. So if you put a big old cardboard box out in the sun and leave it in the sunshine, this is what's happening inside the box. So that's why it's so uncomfortable. Okay. If we switch over to a slightly different kind of analysis, there's something that actually tells you an awful lot about where the gains are coming from. That's this passive gains breakdown. If you go switch into that, you can actually sort of start to see the source. Let me go through and calculate that. And you'll see that there's a couple of different things happening in here. There's the notion of conduction, solar air, and direct solar. And let's talk about all three of those, because those are sort of the big three culprits you tend to worry about in terms of what's going on. Okay. Conduction that's the amount of heat that's actually flowing through a surface. So we'll often talk about a wall having a certain R value or a certain U value. And that's okay. We can really talk about it either way. Just different parts of the world like to talk about it differently. Basically, you need to know that R is equal to 1 over U. Okay, so when we talk about an R13 wall or an R19 wall, anyone have their calculator handy? Like, you know, what's 1 over 13? Any calculators? Lottie, Raj, anyone? So 13 is 0.7?
69.
Okay, how about R19? Actually, I have a pretty good sense. It's almost 1 over 20, right? Okay, so this is the R value. That's the U value. And the way these are actually expressed is, you know, in different unit systems, in the English system, these are BTUs. I think it's per square foot, but it might be per square inch per hour. So what's this a measure of? That's just basically for every square foot of wall that we kind of cut out there, how much heat's going to flow through that wall every hour. Okay, so what happens is the higher the R value, the lower the conductance, less heat moves through in either direction. Our conductance is really, it's bidirectional. It really doesn't matter which way it goes. Okay, higher R value is less, lower R value is more flow. So that's what's going to go on. So what happens is, as we look at the amount of heat that's flowing in or flowing out to the building relative to the outside temperature, changing that conductance, changing the thermal properties of the wall to change either the U or the R, okay, that's going to go through and change the amount of conductance. And that's the direct effect. So when we think about it being 60 outside and we want it to be 80 inside, the reason the heat is flowing out is, or what's resisting it, is that resistance of the conductance. Okay, so that's the first important factor. So if we wanted to try and change that, we go playing around with things that are really changing the R value or the U value of the wall. The second big effect that's actually in here, let's think about that. Well, in this box, you'll notice there isn't any direct solar. Okay, and that's because there's no windows in the box right now. What's happening in our big old box here that really doesn't have much form to it right now, you know, there's really no way in which the solar beams are actually coming through the glass and heating up that space inside. It's completely insulated from that. We don't get any direct solar right now. If we put some windows in, we'd actually start seeing a little bit of effect of that. Because what ends up happening as the sun's rays kind of come on down and they go through a window, as soon as they get through that window and they get into our space, as they're sort of just heating along the air that's kind of in front of the window, that's actually introducing heat into the space. So that's direct solar. Okay, we don't have much of that here. The third and almost even more important type we get over here is something called solar air interaction. Let's talk about that, because that's actually something even our box with no windows has. Here's what basically happens. Okay, you got the sun. These rays are beating down on things. What happens is surfaces that get the sun's radiation go ahead and absorb that radiation. So what happens is, as that sun is beating down on these walls and on this roof, okay, that energy is actually being stored in there. Yeah. Same thing if we have windows and the sun is beating down and actually hits a floor surface, okay, the floor will absorb the energy and then re-radiate it later too. Okay. That whole effect of basically absorbing the energy, heating up, storing the energy, and then re-radiating the energy throughout the day, that's this thing called solar air radiation. So what happens is, after that roof heats up, and it gets all warm, long after the sun is no longer is there, what's going to happen is that roof will continue to radiate energy into the space. It will radiate it this way, it will radiate it that way, it will radiate it in both directions. Okay. But you have that notion of basically heat being captured and then being re-radiated into the space. Okay, so that's solar air radiation. And those are the three things we sort of work with when we start thinking about building envelopes, is really those three different effects. Ventilation is something that, just so that the space isn't super still to move some air, we tend to lose some heat just through having to keep a certain amount of fresh air in the space, and the heated air will actually move out that way. Internal, we're not seeing any loading. Interzonal, we're not yet. But let's go ahead and change some of those things. Okay, so here's the deal. If I went through and I had my building looking at it this way, and we kind of took a look at the temperature, or we looked at the passive gains, whatever it is in here, you can go ahead and take a look at the building and try to understand it that way. But let's go ahead and change things just a little bit. Go back to either 3D editor or visualize, either one of those, and let's actually start messing around a little bit with this whole notion of the zone that's in here. Because right now it's a big closed box. There's nothing else going on there. Let's think about this. If we go through and choose the zone, oops, the one right at the top, we can choose that room and start changing its characteristics. So I'm going to choose that and just talk about what the characteristics are. I can double click that, and I want to do that. What do I want to do? I need to open it. Oh, that's choosing the zone. Hang on. Add zones. Create new zone. Zone properties. Right down there. Jeez. Sometimes you can't find things that are right under your face. So here's the story with zones. There's all sorts of things about the zone and what we're actually trying to use to, just sort of for that individual zone or room, kind of talk about its characteristics. Okay. A very big thing about the zone that we need to talk about is this whole notion of any internal gains. We'll kind of deal with that more in just a little bit. We'll talk about what happens when you put people into a space, or computers, or equipment into a space, and stuff like that. For right now, let's just kind of look at the thermal properties. We'll go back and add the people in just a second. Take a look at what's going on there. So here's the deal. Currently, right now, we have the notion of this box, or this room, being operated 24 hours a day. That is, we're going to care about what the temperature is in the space 24 hours a day. Later on, we'll start saying, we only care maybe from 8 to 5, or 9 to 6, or whatever it is, in terms of when we actually care about conditioning things. But for right now, let's kind of keep it 24 hours. We have the notion of what we're going to consider the comfort band in the building. That is the lowest temperature you're going to tolerate before you kick on the heat, and the upper band, which is the highest temperature you're going to tolerate before you kick on the cooling, okay? And what kind of system you have in there. Now, right now we don't have any system in there, which is why it's overheating or it's overcooling, whatever it is, it's not staying within the comfort band. Let's go ahead and change that a little bit. Let's change that too. We got a couple different big choices in here. We have the notion of natural ventilation, mixed mode, and full air conditioning. Let's think about that. Natural ventilation would be, hey, we can open the windows and cool things off. It's cooler outside, we can, and we'll let that happen. So if it's cooler out than the hot air in here, and we want it to be cooler, we can take advantage of that. Okay. Mixed mode is the notion that we'll sort of go, well, let me say full air conditioning first. Full air conditioning is we'll never open the windows, and if it's too hot, we'll turn on the air. If it's too cold, we'll turn on the heat. Okay, one of those two things. Mixed mode is we'll try and do the best of both. So if it's possible to open the window, use natural cooling, go ahead and do that. Okay. So let's see if we can actually understand what the impact of some of these things are. So for example, let me go for a full air conditioning strategy first. That's kind of the brute force approach we've used in a lot of buildings for the last 30 years. We'll just kind of lock all the doors and windows, assume it's completely airtight, and just turn on the air conditioning. So we'll do that. We have our heat and cold over here. That's okay. Let me go ahead and say okay to this. And again, we don't have any people in there. We're just going to look at the effect of the box and heating and cooling it. Okay. Quite independent of anything going on in the box. So we'll go through and do an analysis. Calculate again. Let me see if I can switch over to another kind of report that will make this a little bit easier to see what's going on. Let me shift over to, you're going to see we still have the same sort of passive gains and passive losses. That hasn't changed at all. That's kind of exactly the same. Nothing's changed there. If we go ahead and take a look at the notion of resources, though, let's see if I can figure out this. Here's what's basically happening inside that box right now with full air conditioning. Here we are in I guess India. What's happening is throughout the year there's a little bit of heating, there's a little bit of cooling going on. But as we go through the year, you'll sort of see cumulatively across the year, and we can make this cumulative or not. Maybe I'll make it not so cumulative, make it a little bit easier to see. We have, in the months of January and February, we're doing a little bit of heating to get the box up. Same thing in December, we're doing a little bit of heating, but through almost all of the year, we're doing an awful lot of cooling. Okay, just to kind of basically keep that space down to where it needs to be, to try and keep it within our comfort zone. So as we go through and look at this, we can look at really what the load is, how much resources we're using really at any time of the year. Or if you want to sort of see what the overall impact is across the year, okay, we can make that cumulative. So we'll get some sort of chart like this, which shows that in a fully heating or cooling based system, okay, if we actually, and write that down. So for full AC, if we try to maintain the temperature range, and what was it? It was like 65 to, I'm not sure what it was. We'll write it down in just a second here. Okay, we're going to basically consume somewhere around 16,105,437, something like that. Now, that's kind of like our worst case scenario, because we really haven't done much of this at all. But let's think about how we can start adapting that and changing that, because there's really an awful lot of things we can. And some involve the envelope, some actually involve the heating and ventilating systems and the set points. So some things we can do. Okay. This is heating and ventilating, just kind of strictly, keeping it, or heating and cooling, keeping the windows closed. What do you think is going to happen if we allow ourselves to open the windows sometimes? Okay, if we, as opposed to always keeping the windows open or closed and always doing it through powered systems, if we go through and try to take advantage of the natural environment, like when the temperature outside would actually allow us to. So. How big a difference do you think that would actually make in a system like this? I'll allow for you. It's probably going to go down. But how much do you think it'll go down? Just by basically having operable windows and kind of opening and closing them at appropriate times. Do you have any guesses?
Does it assume a window area or something? Because we don't have any.
Yeah, in this case, it's not assuming an area. It's almost like we could blow. We can just bring in cooler air from the outside, even through a mechanical system or something like that. So it's not limited to an area. You're right that it should, as we get more sophisticated. How big an impact do you think you can make just really by just introducing natural heating and cooling? Any guesses? Yeah, I don't know what it is right offhand. I'm going to find out too with you in just a second here about really how big the impact is. If I go back to the zones and I edit that zone property, and I just change from full air conditioning to a mixed mode system. Say OK and recalculate that. Okay, now don't be deceived. It looks like it jumped up there, But it jumped up there only because it automatically rescales the graph, which I really sort of hate about this. If I go on back down there, what is it? 16,455. Oh, it's interesting. It actually looks like it got worse. Okay, which, well, I'll live with that for just a minute. Cumulatively, well, think about why that is. All this stuff, there's science behind everything, and a lot of times the effects are a little bit counterintuitive. You have to sort of figure out why it would be that you would actually have a worst case performance. And we can get to, that's interesting. You know what it is? No, it's that number at the bottom is actually wrong because that's not the cumulative. That's actually the same as December. Or actually, no, it's cumulative. Hang on. No, 16,455, 154. Let's try it again. Come back over to full. That's cumulative, that's okay. 16,105. A little counterintuitive. I'm not sure why that is. Let me switch over to a natural ventilation system. We'll see what's happening there. In this case, we're not getting any resource consumption because it's all strictly natural ventilation. So I'm going to put a hold on really why that other one's kind of give me a counterintuitive behavior. I don't really understand that, but we'll dig into that. Okay, let's go back over to more of a mixed mode system. I'm going to shift back, or a full air conditioning system. Okay. What do you think the impact is of, we have this, it's actually, it looks like it was 64.5 or something like that, or 4, all the way up to 78.8. Okay, so that is the comfort range we're going to live with, you know. Actually, my own house, I tend not to like it as cold as 64.4, but I have to wear sweaters and, you know, sweatshirts all the time. Okay. What do you think the impact would be now? Okay. If we were going to go change this temperature range from this, what was considered a comfortable range, to a not necessarily as comfortable range for everybody. Okay, really. Which is going to make the bigger difference in terms of like actually having an energy impact for Delhi? Anyway, is it changing the heating or is it changing the cooling? Okay. Given the cooling problem we're having in Delhi, okay, it's definitely going to be more of a cooling issue here. So currently it's 78.8. Okay. Now someone suggested earlier that it could be okay to get it up to 82 degrees or something like that. Okay. That's actually probably a pretty acceptable temperature for me. I don't know, everyone has a different assumption about that. Let's see what the effect would be. So if I actually changed it to 82 degrees and said OK and recalculated it, let's see what the effect is now. Okay, 16. Nah, okay, there's clearly something broken in the way this is all working right now because it's not actually giving me the behavior I want at all. Something's very odd. I'm not sure what's going on right now because it's on, off. It's on 24 hours a day. Think about that. Something's actually being very, very strange. I don't know. I'll figure out what's going on here. Sometimes my tools vex me, and we're going to go ahead and live with that for right now. But there is this notion of really changing the set points, and really what should be happening? Well, we're going to try a different climate file. That's really very baffling to me. So let me try something a little bit different to see if I can sort of demonstrate what I want you to see. And that is, let's change the location. Let's change it as opposed to Delhi. Let's go flipping that over to, for example, how about a nice cold environment? Well, I'll go to St. Petersburg or something like that. Okay, what'll happen if I go to St. Petersburg and I run the analysis? You'll see I get a very different thing. There it's almost exclusively heating. Very, very little of the year are we doing any cooling. Okay. So again, we can look at that month by month. Okay, or we could look at it cumulatively. But then in terms of this effect of the room itself and what we're doing, let's see if we can sort of like make anything happen here. Right now it's full conditioned air on both sides. The heat's currently set to 64, which is already pretty cold. If I let that be 60, for example, let's see what we got here. What is that? That is 25, actually it's 256, 302. That's 214. Okay, so let's think about that. 256 to 214. Okay, so in terms of the total amount of heat that is being consumed by the building, by basically shifting the set point down, what did I set it down, 2 degrees or 4 degrees, something like that. Yeah, I was actually able to lower the consumption of the building. What is it? It's not exactly a fifth. It's not too bad. Probably about 15% or something like that. So there's different things we can do to the building, one of which is just going to playing around with the notion of building what your comfort zone is with the building. But that's not necessarily the best way to do it. Let's talk about other ways to do it. We actually get into the notion of the building envelope and how we adjust that.